Hi everyone, in this video I am going to explain about binary search. This binary search is one searching algorithm which again uses the concept of divide and conquer technique. Okay, so now in the binary search, the given one key element and given some set of elements, we need to search whether the given key element is present in the given set of elements or not. Okay, for example, suppose let us take this is some elements. Okay, so now given one key element, now we need to search whether this key element is present in these elements or not. What do you mean the key element? Key element is nothing but an important, that means which we are searching. So whichever is important for us, so that we are searching. Okay, so that we are doing in this binary search. So now let us take, so this is in generally, I have not taken any of the elements. So generally there are some elements are there and one key element is there. So this already we discussed this searching technique. So that is what in the brute force technique, in the previous video we discussed about linear search. That linear search uses brute force technique. What we did in the linear search, the given key element, first I compared with the first element. If the key element and this element matches, so then we'll stop searching and we'll return the position where we found. Now suppose this key element is not matches with this one, so then what we are doing, we are comparing the key element with the next element. Again, if matching is not done, again we are comparing this with the next element. So like this, we are comparing the given key element with the all the elements one after the another in a serial fashion. Hence this is also called a sequential search. Finally, we are comparing with the key element with the last element, and even though after checking all the elements, then also we not found, then we'll say it is an unsuccessful search or we not found the key element, and at that time we are returning -1 as an output. Suppose anywhere that key element is matches with a particular element, we stop searching there itself and we'll return that position. So this is what we did in the linear search. So what is the problem in this linear search? It is taking long time. Suppose assume whatever the element we are searching is present in the last position. At that time, we need to search all the elements. Suppose we are having here in this example 5 elements. The last element means how many times I have to compare? 1, 2, 3 and then 4, 5. 5 times we need to compare. Suppose there are 10 elements are there, I have to compare 10 times I have to compare. Suppose 100 elements are there, 100. So n number of elements, n. So that is the time complexity of linear search in the case of linear search. Okay, time complexity. So n. Okay, so to overcome that disorder, that is a time consuming. Which one? Linear search. To overcome that, we go for another technique called binary search. What is the technique what we are using the binary search is, here in order to apply this binary search, we need to sort these given elements. First, we need to sort the elements and then only we can apply the binary search. If the elements are not sorted, then it's not possible to apply binary search. Okay. So what to do in that case? First, you sort the elements and then you apply the binary search. If you sort the elements, what happens? So now we can easily find out the key element. Okay. For example, assume in a classroom. In a classroom, both boys and girls are sit and scattered. Okay, everywhere, wherever they want. So at that time, if I want to search any one particular student, I need to search in the entire classroom. I need to search. So it takes time. Suppose if I made the students to sit boys one side and girls one side, then suppose if I want to search any one boy student, then I no need to see at the girl side. I need to see only at the boy side. That means instead of checking the entire classroom, now I need to check only the half of the classroom. This is how it is efficient when the elements are sorted. Same technique, binary search. So it will either search in the first half or in the second half. Okay, that we will see with an example. Now let us take, this is the example. So I'm taking the 5 elements 10, 20, 30, 40, 50. As I said, for this binary search, element should be sorted order. Either it will be descending order or ascending order. So I took these numbers and assume key element is 30 in this example. So now what we do in the binary search, we will take one leftmost index. Okay, here which is this is the 0, 1, 2, 3, 4 is the index. Now which is the leftmost index? L. This is the 0 is the leftmost index and 4 is the rightmost index. Okay. Now what we will do, first we will identify what is mid position. How to find mid position? So now this I know the leftmost, this is the rightmost. Now mid element I want to know. So mid position, mid is equal to what? Mid position is equal to 0 plus 4 divided by 2. But here left plus right. So okay, leftmost index, rightmost index, then divided by 2. This is what we'll get mid position. Now in this case, it is what? 0 plus 4 divided by what? 2. So that is equal to 2. This is the mid position. Now I got this is my what? Mid position. Mid position is this one. Okay. So now what I will do, always in binary search, always we will compare the given key element with the mid element. That means element stored in the mid position. Element stored in the mid position 2 is what? 30. So always we'll compare the key element with the mid element. Now in this case, key element is 30, mid element is also 30. So here match is successful. So that means I found the key element in the position mid. So I will return the position mid. Okay. So I return this position mid, that is 2. That means I found the key element in the position 2. This is one case. Now let us take another example, same example. Now I will take key element as 50. So now again same thing, this is leftmost index, rightmost index. Now again I have to calculate what? Mid position. So initially mid position was 2 only. So that means my mid position is now this one. Mid position is 2. Now again, always what we'll do, always we'll compare the key element with the mid element. Always we'll compare the mid element. Now when I compare this one, matches are? No, it fails. These two are not matches. Now what to do? Now since it is already sorted, now see, these are the elements which are lesser than the what? Mid element, and these are the what? Greater than the mid element. Okay, greater than the mid element, and it is lesser than the mid element. Okay, now I need to find out, since these all the elements are sorted and the key element is not equal to the mid element, now I need to decide whether I need to search either in the first half or in the second half. Okay, so how to decide? Now I need to check whether the key element is lesser than the mid element or not. Suppose key element is lesser than the mid element, I need to search only in the first half. No need to search in the second half. But in this case, what key element is 50? 50 is greater than the mid element 30. Since it is greater than, now I need to search only in the what? Here I don't want to search in this first half. So now I need to search only in the second half. So what I will get, now in second half means I will get only these two elements, 40, 50, and this index is what? 3, 4, and again my key element is what? 50 only. Key element is 50. So now what I have to do now, in this case, leftmost index is what? This is leftmost index, and this is my rightmost index. Now again what to do? Calculate what? Mid position among these two. Mid position is what? Now left is 3, right index is 4, 3 plus 4 divided by 2, 7, 7 by 2. Now we need to decide. When I do 7.7 by 2, actually I will get what? 3.5. Now I need to decide whether I take lower limit or upper limit. Now if I take lower limit, so there is a 3.5, 3.5 lower limit is what? 3. That means now I got mid position is what? 3. So that means now here I got, this is my mid position. Mid position is what? My 3 is the mid position. Now again, always do what? In our binary search, always will compare key element with the mid element. Here also again what I will do, I will compare key element with what? Mid element only. Now again here these two matches, no, doesn't matches. Now again what to do? Now again I need to check whether I need to search in the first half or second half. That in this example I don't have any left subarray. That means the first part. Now I need to search only the second part, as it is the key element is greater than the key one, okay, mid element. So what I will do, so now I need to search in this case. Okay, so here 50 this is, now this index is 4 and this is my key is equal to what? 50. So now again in this case, this is my leftmost index, this is my rightmost index. Now again I need to calculate what? Mid position. For this mid position what? Left is 4, right is 4 divided by 2. 4 plus 4, 8. 8 by 2 is 4 only. That means this itself is my mid element. So now always in the binary search what we will do? We will compare our key element with what? Mid element only. Now it is successful. Okay. So now we found the element at the mid position, return mid. Okay. This is what we did. Okay. What we did now here, The same way now we are writing the pseudocode for this, that is algorithm. So now I am given the name binary underscore search, array to be passed, array in which we need to check the key element and the key element. These are the parameters to be passed. Okay. So now initially what we did, as soon as we take the array, we took the leftmost index, rightmost index. Generally, which one we have to take as the leftmost index? For L, okay, that is the 0th one. Last index, that is n minus 1 as 1, R. So I will take L. So this is what initially 0 and rightmost index is what is nothing but n minus 1. Okay, this is what we took. So next what we did, now whether we divided this into two halves like this, first half and second half, we find the mid element. Yes, we did this one. We got this mid position. This is the first half, second half. Again, after that, again we got these two, second half into search. So again we calculated the mid and then we get the one more half. Only one half I got. So again, whether we divided here? No. Why? Because after only one element, if either find or not find, suppose here also doesn't match us, so it was unsuccessful. Successful search. So we need to stop that. That means we divided more than one elements, we divided more than one elements, no, we not divided. Okay, that means we need to check whether more than one elements are there or not. So condition is, if you see here 5 elements are there, here 2 elements are there. So if L is less than R, L value 0, R value 4, L is less than R, L is less than R equal to R, there is one element. Till one element we need to search. See, why we are not search here? Why we not search here? Because I got only one half. Why we don't get this half? Because if you take this one, L is greater than R. Okay, so we should not take it. Okay, so either L should be less than R or L should be equal to R. Then only we are comparing the key element with the mid. So what I will do, I will check while L less than or equal to R, then do. That means when less than or equal to R, what we will do? First what we did, after this one, we check the mid. We calculate the mid position. So mid is equal to what? Left plus right indexes divided by 2. Then what we did? Then we always compared what? Key element we compared with what? The mid element. So comparison, if you have used, if key is equal to A of mid. If this is true, these two matches. If these two matches, in this case, what we did? We return the mid position as what? Answer. So return mid position. Return mid. Else, suppose in this case now, if the key element is not equal, then what we did? Now we need to decide whether we need to check in the first half or the second half. That we need to decide. So how to decide? Now again I need to check key element is less than mid or not. So for that, else if what? Key is less than A of mid. I am checking. If this is true, suppose key element is less than the mid, where I have to search? I need to search in the first half. In the first half means, so left remains same, but R remains same. What? R becomes this one. So R becomes what? Mid minus 1. So I am changing R is equal to mid minus 1. Else, suppose this condition is also false. That means no, this condition is key element is less than this. No. At that time, what we have to do? We need to search in this half. When this half means, now, see, R remains same, but only left is going to change. Where the left comes? After the mid. That means mid plus 1. So now we have to change only what? L is equal to mid plus 1. Okay. So that's it. This is the end if. Okay. Then end while. So then, finally, after checking all these things also, suppose if you not find, then finally what you have to do? Return minus 1 indicating unsuccessful. This is the algorithm for what? Binary search. Okay. So now we will do analysis for this one. Analysis. What is the first step? Decide in the problem size. Problem size what? Now I am searching only one key element. Always we are searching only one element at a time. But we are searching this key element in how many elements? Among the 5 elements, among the 10 elements, among the 100 elements, in how many? Okay, that depends. So the number of elements in which we are searching, that is the problem size. That is what n. Okay, so now second step is to identify the basic operation. Here, which is the basic operation? Generally, how we will decide whether the key element is present or not? Always we are doing what? Always we are comparing the key element with the mid element. Key element with the mid element. Key element with the mid element only we are comparing. So comparison of key is equal to A of mid. So this will be our what? Basic operation. Okay, so comparison operation, key is equal to A of mid. This will be the basic operation. third step. So we need to decide whether we need to find all the three cases or only the average case. Here, see, in this case, we executed comparison how many times? See, exactly one time. This will be the best case. See, here, in this case, we compared how many times? 1, 2, 3 times. When the key element is present at the last. Similarly, if the key element is present at the first also, we need to execute 3 times. So, worst case happens in 2 situations. Situation 1, when the key element is found at the first or at the last. At that time also, we need to execute more number of times this basic operation. Or key element is not found also, exactly this many times only we need to search. Okay, let us say this was 60. Suppose this is key element is 60 now. Okay, so now again key element is false. Again key element is false since greater here only. Again false. So again 3 times only. So was best case. So best case when occurs when the key element is matches with the mid position. At that time we are doing how many times? Only one time. For that I am writing C best of n belongs to what? Big omega of 1. This is my what? Best case time complexity. Now let us say for the worst case. Again, worst case occurs in 2 situations. Situation 1, successful search. In successful search, if the key element is found is either in the first position or the last position, that will be the worst case in the successful search. In the unsuccessful search, the key element is not found. That means element is not found. At that time also, we have to execute the comparison operation same number of times. So now I will write at the C worst of n. At the C worst of n, now how many times we are doing comparison operation? Now, comparison operation at a time, how many times here? At a time, only one time. At a time, only one time. At a time, only one time. So, at a time, I am doing only one time. But, so whenever it is, see, worst case means either it's not at all in the mid position, either in the first half or second half. So, that means if either I have to search in the first half or in the second half. So that means any point of time I am searching only in half of the array instead of searching the entire array as in linear search. So since I am finding in any one half, I am not taking 2. So C of n by 2. That means see, this is half. In this half only I am searching. In this half I am not searching. Suppose if you are searching in this half also, then you need to write here 2. Number of subproblems is 2. Here even though we are in 2 subproblems, we are not searching in both the subproblems. We are searching in only one subproblem. So here 1 into C of n by 2, that is C of n by 2. N by 2 why? Because almost half of the elements, so n by 2. Now comparing this in this equation, we know that what? Number of comparing this equation with what? T of n is equal to what? T of n is equal to A into T of n by B plus F of n. You compare this, now A is equal to what? 1, B is equal to what? 2, and F of n is equal to what? Generally the problem says this is equal to 1, n to the power of d is equal to 1. This can be written as 1 to the power of 0 is equal to 1 only. That means therefore d is equal to 0. Now I know A value, I know B to the power of d value. A value is 1, B is 2, 2 to the power of 0. This need what? If 2 to the power of 0 is 1, 1 is equal to 1 only. That means now I have to use C worst of n belongs to big omega of, what is the formula according to the Master's theorem? N to the power of d log n to the base b. So now this belongs to big O of n to the power of d value is 0, log n base 2, b value is 2. So that is hence C worst of n belongs to big O of n to the power of 0 is 1, 1 into log n is log n. So log n to the base 2. So this is the time complexity of the worst case. Hope you people understood. Thanks for watching. If you have any questions, please write in the comments. Thank you.